All right, we are in section 9.5, looking at linear differential equations, specifically first order linear differential equations. So this is a specific type of differential equation that can be written in the following form. So it can be written, oops, not like that, like dy dx plus p of x times y equals q of x. And this is where p and q are continuous functions on a given interval. So this is just the form of a first order linear differential equation, and what we're going to be doing here to start off is deriving a formula, a process, to be able to solve these, and then we'll do several examples actually practicing with it. Okay? So every first order linear differential equation can be solved by multiplying both sides of this equation by a function I of x, and this is known as the integrating factor. Okay, so the integrating factor I of x, we're going to be multiplying that, and that's going to be the key to solving these problems. So we need to find what I of x is. Because if we can find what this is, that's going to allow us to solve these. So we want the left-hand side of the equation, when multiplied by I of x, to become this expression. Okay? Now, emphasis on this is what we want. Okay? So what we can do is say, okay, well, take the left-hand side of the equation, multiply it by I of x, and I want that to be equal to that right-hand side, to I of x times y prime. Okay, so let's multiply the right-hand side by I of x as well. And the right-hand side, if you recall, that was just q of x, right? So this is, so I of x times y quantity prime equals I of x times q of x. Okay, so we multiplied the right-hand side by I of x. Now, if we integrate both sides of this, well, integrating the left-hand side, that's just going to undo the derivative, so that just leaves us with I of x times y, and then on the right-hand side, we have the integral of I of x times q of x dx. So, then we get y of x, should say, as a function of x, equals 1 over I of x times the integral of I of x times q of x dx. Oops. Okay, so we would get that. Now to find I of x, we're going to expand our earlier desired equation. So that's this one back up here. Okay, so we're going to go ahead and expand that, multiply I of x out. So that's going to give us I of x times y prime plus I of x times p of x times y equals, now on the right-hand side, we look back up here, this is the derivative of a function of x times a function of x, so we are going to be using the product rule here. So this is going to be I prime of x times y plus I of x times y prime. Okay. And now, if we look, we have I of x times y prime here and here. Subtract them away. So all we have left is I times p times y equals I prime times y. Divide both sides by y. we get I times p equals I prime. Now, what can we do with this? Well, if you look over at the next page, this is a separable differential equation where x is the input variable and I is considered the output variable, kind of like y in a general function. Okay, so we can rewrite this. So write this as I of x times p of x equals di dx. So instead of I prime, I'm writing derivative of I with respect to x. And now write this as a separable differential equation. So I'm going to bring the dx over here, divide the I over here. That's going to give us p of x dx equals di over I. And now we can integrate both sides using that technique of the separable differential equation. So if I'm going to go ahead and just switch the order of these, make the i's come first. But antiderivative of 1 over I, that's going to be ln of the absolute value of I equals the integral of p of x dx. And we just have to leave that because we don't know what p of x is. And then this gives us I equals a times e to the integral of p of x dx. Now, for the a, if you want to just ignore the a for a second. So we raise both sides to the ln power, so, to the e power. That gets rid of the ln, right? So I did that, and did that. And then to get rid of the absolute value and to get rid of the arbitrary constant, we do a trick like we did at the very end of 9.3 of that section. This is where a equals plus or minus e to the c, so that arbitrary constant. Okay, so that gives us our arbitrary constant a. However, in this circumstance, because we're looking for a particular solution to this differential equation, we don't need the arbitrary constant to be arbitrary. So since we're looking for a particular solution, and not an arbitrary one, we can pick whatever we want for the c value, for the a value, what have you. So we can let a equal 1. And if we let a equal 1, that simplifies our formula immensely. So we get I of x equals just e to the integral of p of x dx. Okay, so this formula for I of x, and I have it again written down here. This formula for I of x is what we need to be able to now solve these linear first-order differential equations. Alright, so let's go ahead and start looking at some examples here so you can see kind of how this process is going to go. Okay, so let's solve this differential equation. So let's identify our pieces here first. So p of x, that's going to be 3x squared. Oops. Q of x, that's going to be 6x squared. And then we can find I. So I of x, that's going to be e to the integral of 3x squared dx. So that's e to the x cubed. Okay, and again, we don't need that arbitrary constant because we just assume that it is whatever value makes it go away. So let's go ahead and take this information here, and we're going to multiply both sides by I of x. So this is going to give us e to the x cubed times dy dx plus 3x squared e to the x cubed y equals 6x squared e to the x cubed. Now the left-hand side, the reason we're multiplying by I is because we can specifically write this as the derivative of I times y. So derivative of e to the x cubed times y, and that equals 6x squared times e to the x cubed. Okay, again, that was the whole point. The whole point is that we're multiplying by I so that we can get it in this form. So e to the x cubed times y. So I times y. Now we can integrate both sides, because this is now going to be treated like a separable differential equation. So we're going to get just e to the x cubed times y equals the antiderivative. You can do a u sub on this one to get it with u equal to x cubed, and you'll get it pretty quickly, but this is just going to be 2e to the x cubed plus c. Okay, and then because this is our final solution, we will end up leaving the plus c in there in this circumstance. So then divide away that e to the x cubed term to isolate the y. So we get y equals 2, right, because you divide by e to the x cubed there, plus c over e to the x cubed. And then if we wanted to get an initial value problem, we could solve for what that c value is. But this is our general solution for this first order linear differential equation. Okay. So let's go ahead and look at another example. So find the solution to this initial value problem. So for this one, the first thing we have to do is you have to notice that the formula that we were given, we always have to have y prime with no coefficient on it. So in order to use this process, we have to divide. So divide by x squared to put it in standard form. Because if you try to work with it like that, it's not going to work. We have to have that y prime being isolated first. So let's see what this gives us. This gives us y prime plus 1 over x times y equals 1 over x squared. And this is with x being greater than 0. Okay, so let's see what we have here. We have p of x is 1 over x. Q of x is 1 over x squared. And I of x equals e to the integral of p. So that's going to be e to the ln of x. We don't need the absolute value here because we are assuming that x is positive. So this is actually just going to be x. So in this case, I of x is just x. So let's go ahead and multiply I by both sides. So that's going to give us xy prime plus just y, right, because we have x over x, equals 1 over x. Okay. So this gives us I times y prime, again because I is x in this case, equals just 1 over x. And then we can integrate both sides. So this is going to give us xy equals integral of 1 over x dx, which is just ln of x plus c. So we're going to get y equals ln of x plus c over x. Okay, just divide that x term over. Right, so we just divide there, and then divide that by this side as well. Now that would be our general solution to the differential equation. But in this case, we do have an initial value problem, so we need to actually use the initial value here. So y of 1 equals 2. So let's go ahead and just plug that into here. So we get 2 equals ln of 1 plus c over 1. ln of 1 is 0. So that's just c over 1 equals 2, so c is 2. So this gives us y equals ln of x plus 2 over x. And that is the solution to this differential equation, to this initial value problem. Right. So let's look at one more. So again, just utilizing this same process. So we have y prime plus 2xy equals 1. So let's first find I of x. That's going to be e to the integral of 2x dx. That's just going to be e to the x squared. So we're going to multiply that by both sides. So we get e to the x squared times y prime plus 2x e to the x squared times y equals e to the x squared. On the left-hand side, that gives us I times y prime. And then that just leaves us e to the x squared on the right-hand side. So we're going to get, when we integrate, e to the x squared times y equals integral of e to the x squared dx. Now this integral on the right hand side, this is actually not integrable as is, so this one is not integrable as is. So what we're going to do is we're going to leave it. This is not something that we can solve at this point, so we're just going to leave that there and just write our solution implicitly in terms of that integral. It will need an arbitrary constant because we would hypothetically integrate it and get a plus c. So then I just divide both sides by the e to the x squared. So that's going to give us y equals e to the negative x squared, right? Because I can do that instead of writing it as a fraction, times the integral of e to the x squared dx plus c times e to the negative x squared. Okay, so it is a little more rare that we have a solution with an integral still in it, but that's just, that integral is not quite in our toolkit that we're able to solve. So sometimes you will see that we encounter differential equations that just have integrals in their solutions because we know how to get to that point, but we don't know how to then finish it off, right, to write the actual integral value. Okay, so that's the end of section 9.5 and the end of chapter 9. So pretty short chapter for us here, just an introduction into the concepts of differential equations. You would see a lot more with these concepts